The concept of frequency response is similar to another response that we met when you are dealing with continuous time LTI systems. The one that we refer to as the impulse response, H of t, whereby we said that if we know a system, the system's response to an input x of t defined by delta of t, then we say that the output will be equivalent to h of t, and this completely characterizes the system response to another arbitrary signal x of t, even when it is not equal to this one. And we said that the output y of t is equal to h of t, particularly when, of course, when the input is delta of t, and the delta of t is the one that we defined as the unit impulse signal. The h of t, we called it the impulse response. Now we are going to use the similar concept and say that the frequency response is going to be borrowed directly from the same concept, whereby we are going to describe the frequency response to be the Fourier transform of your impulse response h of t. And you are saying that if you have now your signal is in frequency domain as x of omega, and you are taking it through a Fourier system that is defined by h of omega, then the output will be y of omega. And now, as you said about convolution, when we are talking about the time domain, we said that y of t is going to be equal to the convolution of the input signal and the impulse response. But now in the frequency domain, y of omega will be given by the multiplication of the input signal and the system's impulse or frequency response defined by h of omega. We are simply saying that this agrees with what even the properties that we have said, that we said earlier on, that multiplication in time is equivalent to, or rather, multiplication in frequency in a frequency domain translates to convolution in time domain. So these two agree with what we have already said, and therefore that is how we are introducing the frequency response. And we are saying that the frequency response is actually considered to be h of omega, or the response of the system to an unit impulse signal that we are going to define as delta omega. But now we are going to be defining delta t, but we are going to be defining this one now in omega, and you're going to see that it is equivalent to 1, that is a Fourier transform of d of t from time domain. It becomes 1 in a frequency domain. So we have already developed equation 567 that says that the Fourier or the frequency response of a system is equivalent to, okay, rather this is what I have just said up there, that if you have input x of omega, and you take it through a system that has frequency response h of omega, then it is going to give you the output y of omega. And therefore, if you just make h the subject of the formula, you are going to find that h of omega is going to be defined by equation 57. And this is the one that we refer to as the frequency response of the system. So remember that in time domain, we called it impulse response. But now in frequency domain, we are calling it frequency response. So this is a term that we adopt, and it's something that we are saying that it completely describes the system's response to any arbitrary input. Because once we know the system responds to a unit impulse signal, we can always be able to describe the output given an arbitrary signal x of omega. So we are in addition saying that if our unit impulse response signal is applied to an LTI system defined by h of t, then the output will be h of t if we apply the unit impulse signal. And that is, this is the one that we described as the impulse response. But now in time domain, we're saying that the impulse response translates to frequency response h of omega as described in question 567. And we're saying that you can always have an arbitrary signal x of t that will be translated to h to x of omega. And therefore, if you take it through the same system that is defined by h of omega, then you are going to get the output y of omega that is simply a multiplication of the input and the frequency response of the signal. But remember that in the time domain, we say that the output would be given by a convolution of the two signals, the input and the impulse response h of t. Now we are saying that if we define our h of omega to be having two terms, one is the magnitude and the other one is the phase, then you're saying that the magnitude is called the magnitude response of the system, and the phase term theta h is defined as the phase response of the system. Now, similar to what we did with the continuous time signals, that we said that h of t completely describes the system to an arbitrary input. Therefore, we are following a similar idea that we did that time, and I'm going to skip this to show that h of omega, that is the representation of the system in frequency domain, the one that we are referring to as the frequency response, they completely describes the signal, or rather, completely describes the system to any arbitrary input. And you're saying that if you just follow through the derivation that you have shown, you're saying that the behavior of a continuous time LTI system in the frequency domain is completely described or characterized by h of omega. And therefore, once we know h of omega, we can always be able to describe the output y given any arbitrary input x of omega. And now to sum it up, we are saying that the magnitude response of the output will be given by this multiplication of the magnitude response of the system and the magnitude spectrum of the output. And similarly, the phase response of the system is the summation of the phase spectrum of the input and the phase spectrum of the system, the one that we are describing as the phase response. So those two are particularly important because they help us to describe the system if we know the magnitude and the phase of the system that is defined from its frequency response. We are saying also that the magnitude response h of omega described by magnitude of h of omega is also referred to as the gain of the system. For a distortionless transmission through an LTI system, we require that the output or the input sent to the system is reproduced at the output, although its amplitude and the amplitude may be different or the time may be delayed. And that condition is described by equation 579, that K describes the gain of introduced by the system, and the TD describes the time delay that is introduced by the system. If this condition is not met, then the system is said to introduce distortion to the transmission. So we are saying that, just to get it clear to you, that here we have a system described by h of omega, or h of t in time domain, that you have your input x of t and you have output y of t. We are saying that the output at y of t may introduce some gain uh, to to the input x of t, and also there may be slight delay to the time, such that the signal might be input at time t is equals to 0, but when it is received at y is equals to t at the output, then there is a delay that is equivalent to x of t minus td or t naught. So that kind of a system, despite introducing a variation in the magnitude of the output signal or delay in time, that signal is considered to be distortionless. Otherwise, if it is if it does not meet those two conditions, it is said to introduce the distortion. They are saying now that the figure 5.4a and 5b illustrates a system that can introduce a change in gain or a delay in the signal. And so here we are saying this is our input signal x of t, and the output is y of t. They're saying that this signal may be reduced by a factor k, that is reduced or increased. It might be here, k might be bigger than 1, or k might be less than 1. But the condition that we are saying is that k must always be bigger than 0. So if it is not bigger than 0, then we say that the system is introducing some distortion. The other thing is that if the only thing that the signal does is to introduce some delay, that initially the peak of the signal happened at time t1, but the signal that we are receiving on the other end is coming at 1 second or 2 seconds delay, which is at t1 plus 2 or 3, and 2 being the td. That system is said to be distortionless. We can characterize such a system, such a distortionless system, in the frequency domain by taking the Fourier transform of our signal, of our equation 579 in both sides, and that will characterize our system described by K and TD, as you can see in this equation 580. And from that equation, we can be able to find the frequency response of that system, of that distortionless transmission system. And it is just a matter of time that, or just a matter of identification, that from this system, we have, since we said that or y of omega over x of omega gives you the frequency response of the system, h of omega. Therefore, we can just identify our x of omega here and y of omega. And when you divide both sides by x of omega, we are able to identify that our h of omega is given by k e minus j omega t d. And td is the time delay that was introduced by the system, and k is the gain. So what do you observe? That the amplitude of our frequency response h of omega is constant to k, and k is the gain that the system introduces. And the other thing that you observe is that the phase of our frequency response must be linear. Is simply a function, is linear with the frequency. So you can say that in this case, it is negatively decreasing. And therefore, if you are to draw the system, or to draw the frequency the phase response of the frequency response, rather, the phase of the frequency response, we can actually see them as drawn in figure 5.4c, in figure 5.4d as described. So we are saying that the magnitude of our frequency response is constant, having constant amplitude equivalent to k. So this you can see is the magnitude of our frequency response. And on the other hand, we are saying that the phase of our frequency response is linear, because we have said that theta h, a function of omega, is equal to minus j omega td. So we can simply identify here that our slope is negative td. And that simply tells you how that the condition for distortionless is satisfied. But that is as understood or as expressed in the frequency domain. So what we have seen above here is that if the conditions for distortionless transmission are not met, then we are going to have amplitude distortion and phase distortion. And you want to characterize each of them. And you are going to say that when the amplitude spectrum of the system is not constant, as described by this equation here, then assume it is not constant, probably it is decreasing, or probably it is decreasing. That means that some frequency components are given some gain, sufficiently gained. Assume this is your signal. Therefore, as frequency, okay, well, I think I should not draw that. Not exactly what we want to say. So, if higher frequencies are given different gain than lower frequencies, that means that probably someone speaking with soprano. I believe you might have observed that. Soprano is someone with a lower frequencies and bass. If the amplifier, which is the transmitter, is not having a constant gain, therefore you might hear that the audio that is coming from the bass is audible, whereas the higher frequency components of the signal, of your audio signal, are not audible, like soprano. So I think that I have had for me, particularly when you're listening to some speakers or tutors that cut off the higher frequency components. That is simply because the amplifier might not be having a constant gain uh, 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 in its transmission of the audio signal. So having said that, we can also characterize, talk about the, of course, that kind of distortion that arises due to non-constant gain is called amplitude distortion, such that the different frequency components of the input signal are transmitted using and are given different gain or different attenuation from the others. And I have given you the example of a bass having a lower frequency has probably a gain of 10, whereas the soprano, I don't know if that is how we write soprano a long time. Soprano, which has high frequency, might receive a lower gain of, say, about say 2, and therefore what you might notice is that this signal is much more audible than this signal, not clearly audible. So that is an example of amplitude distortion that says that different frequency components have different amount of gains when they are transmitted through a system. The other kind of distortion that arises the phase distortion, that says that when phase spectrum theta h of omega of the system is not linear. We have said that it should be linear, either the one that you have said that is varying, the slope is negative TD or something like that. If it is not linear, then the output of the signal has a different waveform than the input signal because of different delays in passing through the system for different frequency components of the input signal. And this form of distortion is called phase distortion. We, of course, were able to figure out that we can be able to express a continuous time LTI systems using linear constant coefficient differential equations. We found that earlier. And therefore, we are saying that if you can be able to represent such a signal using the constant coefficient differential equations, that is in time domain, then equivalently we can apply the Fourier transform on both sides, and of course apply the properties that you have already learned, that of the linearity and the time differentiation property. You apply, so you perform Fourier transform of this system, and when you do that, you are able to find the frequency response of your system as expressed without necessarily going into the details, but this is something that all of us can do, and we are going to be able to see that we can be able to describe our frequency response of the system that is described by linear constant coefficient differential equation as expressed in the frequency domain, which is expressed as seen in equation 585. And we can see that this is a rational function of omega. So we have introduced that the constants now, bk and ak, are now functions of omega, and we are saying that this is a rational function. That means that you can be able to express each of the numerator and the denominator as two integers, maybe 2/3 or something. This is what we call as a rational function of omega. And you're saying that the result of this equation is the same as that one that can be obtained using the Laplace transform. And what we are saying therefore is that this is a very significant realization, that we can be able to define the frequency response of a system even if it is described by a differential equation as we have seen above.